efficiency done? Taylor, did you have one we didn't get to?
I think it was in homework number 7.
Okay, so that's on, I think, the 1.7 introduction to continuity.
No, that one was with Powers.
Okay. So,
Number 47.
47 on
On page
53. Okay, so 47. Yep, I'm with you there. Okay, so it says, oh, this is the rate capital R at which the population in a confined space increases is proportional to the product of the current population P and the difference between the carrying capacity L and the current population. Oh, all these things we have no idea what they mean, but that's okay. So what that's, if we translate this, and this is something you're going to have to be able to do. So the rate, capital R, at which the current population is changing, is proportional to the product. So proportional to is going to be K times. And then we want the product of two things. It's the product of the current population, which is P, and what we're multiplying that by is the difference between the carrying capacity L and the current population. So that's what that's going to look like. That make sense? Okay. And so part A is write R as a function of P, and we have done that. That's what we've done there. And part B, sketch R as a function of P. So the idea here is big picture. When you multiply this out, the P's are going to multiply each other, and that's going to be a negative P squared. With it? So that's going to be a parabola that opens down. So the R is going to be our independent variable. The P is going to be our dependent variable. I would leave it in factored form like it is here. So these are multiplying. So when they will be equal to 0, the P-intercepts will be when P is equal to, if we set this equal to 0, and P could be 0 because K is a constant. So if Kp is 0, then divide by K, P equals 0. So we're going to get a P-intercept of 0. And likewise, this L minus P could be 0, in which case P could equal L, whatever L is, I don't know. That's what L is. So these are going to intersect. So we have a parabola that's going to open down and has these as x-intercepts. Oh, you got it. There it is. Crazy. We actually do a lot with this kind of stuff in BC calculus. Hang on until next year. What else?
Can we do 11?
11. Do you know what that is, or do I need to scrounge it up?
I don't know what one is.
Is it, do you know if it's on this same homework?
No, it's on homework 8.
Homework. Okay, so you got a big old rational function. And we want the end behavior, does that sound right? No, I'm sorry, we're the wrong one. Which function dominates? Does that sound right?
I think it's on page 56.
Okay. We're the wrong page then.
It's with continuity.
Okay, oh, okay. Yeah, we'll look at it 11. Show there's a number C. Oh, yeah, I got you. So So we have f of x is equal to x to the third, is that? Plus x squared minus 1. And we want to know that there's a c in between 0 and 1, so that f of c must equal 0. Now notice that in the directions they are not asking you to actually find what that is. They just want you to show that this must be equal to 0 somewhere in between there. So because of that, this is really, they're trying to push you towards using the intermediate value theorem. So remember, the intermediate value theorem has 3 conditions. It's got to be a continuous function. Do we know that this is continuous? Why? Because it's a polynomial. And we know it's got to be on a closed interval. Well, we can see that because of the or equal to. And we want to find something that's equal to 0 in between f of a and f of b. So what we need to do is show that, figure out what f of 0 is, what f of 1 is, and if 0 is in between those y values, then we can say because of the intermediate value theorem, it must equal 0 somewhere in there. I don't know where, but it's got to be somewhere there. So that's the purpose. And that's not hard to do because you plug in 0. You can see that f of 0 is a negative. And f of 1 is 1 plus 1 minus 1 is a positive. So since f of a is negative and f of b is positive, then the function must equal 0 somewhere in between 0 and 1 because of the intermediate value theorem. That's what they're trying to get you to think. What else?
We do number 7 on homework 8.
7 on homework 8. Am I on the same page still, or?
Yeah.
Who knows? So is it something like, is the function continuous on the interval as 1 over cosine x? Okay. So our function is, on number 7, 1 over cosine x. And our interval is 0 to pi. And the question is this function continuous on that interval? So is f continuous on that interval? So remember, what we're looking for, so what you look for is the only way this can be discontinuous, since this is a continuous function over a continuous function. The only way this can be discontinuous is if this denominator is 0. Now you got to think, where is cosine equal to 0? Let's see. Pi over 2, 3 pi over 2, all the over 2's. Well, there's a pi over 2 in between here. So at pi over 2, cosine is 0, and that's going to be 1 divided by 0, which means it's going to be undefined. There's going to be a vertical asymptote there. So is this continuous on this interval? The answer is no. And I don't think they asked us, but where it's going to be discontinuous at x equals pi over 2. So that's what we're looking for there. Now there's other more exotic functions, where it's not quite that straightforward. But on this one, we're just looking to see where the denominator is 0. What else? 33. So 33. Let's see. So 33 is saying 0.6 milliliter dose of a drug is injected, that sounded like running right problem, into a patient steadily for half a second. Ooh, this is tough now. So we're going to inject 0.6 milliliters, but it's not right at once. It's going to be over a half second. So this is that sadistic nurse that's going to make you feel. I digress. It didn't say that in the problem at all. So it's going to steadily inject that for half a second. At the end of this time, the quantity Q of the drug in the body starts to decay exponentially at a continuous rate of 0.2% per second. Using formulas, and we're thinking now this is going to be a piecewise function. Okay, express Q as a continuous function of time t in seconds. Okay, so Q is going to be, well, we're going to have from, for that first half second, we're going to inject 0.6 milliliters at a steady pace. So that means like linear. So we're thinking slope and y-intercept. So y-intercept is going to be, so if we're visualizing or thinking in our head, this is how much of the medicine is in our body, this is time. We're going to start with 0, and when we get to a half, we're going to have 0.6 milliliters in there, and that's going to be injecting that steadily. Is that okay? So what we need, we got a y-intercept, we need a slope. What's our slope going to be? Ooh, not an easy question. So it's, yeah, it's going to be 0.6, this is the rise, over, say, 0.5, that's going to be the run, I think. Does that look okay? So we multiply top and bottom by 10. I think we can even call it 6/5. Or how good are you? Well, I shouldn't even ask this question. How good are you with fractions? I know the answer to that. 1 1/5, which is also 1.2. Is that okay? So we could, if we want, call it 1.2t and then plus 0. You okay with that? That's just that straight line going from the origin up to a half second and then 0.6 milliliters. Okay? Now it's going to decay from that point on, it's going to decay exponentially. Okay, so now it's going to decay. And we want it to be continuous, so these have to connect. We said it is decreasing by, what did they tell us? By 0.2% per second. 0.2% per second. And this is continuously. So what kind of exponential are we thinking? A-perch, yeah, exactly. So we're thinking the amount is going to be the PE to the RT, or whatever you can remember, this is going to be base Euler's number. So if it's 0.2%, what's going to be our R? What's that going to be? 0.002, because we got to change it from a percent to a decimal. So that's going to be, and it's decreasing, so what is that going to tell us? It's really going to be a negative. Now we need to know this value here. And to get the P, what do we need to know? The initial value. But we have to be a little careful, right? Because our initial value is going to start at 1/2. That's when the exponential part starts. Does that make sense? Now we can fix that. Let's do this. Because now when t is a half, our time is going to really register as 1/2 minus 1/2 is 0. So that's how we can make the initial value be, in our mind, 0. And so this is going to be e to the 0, which is 1. And how much do we want to say, how much medication is in our body at the start of the exponential decay? 0.6. Oh, what a crazy hard problem. And this is from, we're going from 0.5 to forever, or we have to really determine that. And I guess it's kind of bad form to make those both or equal to. It would be wrong because they agree at 0.5. Does that make sense? Ooh, that was, that's not the answer? What do they come up with?
They have, the top is the same, and then they have 0.6 e to the 0.001, and then multiply, then e, no, down, less, sorry. Then e to the negative, like this. Multiply that.
Multiply this?
Yep, by e e to the negative 0.002 t. Yeah, see, I got the top, and then I got what you got, and then I looked back to see if I was right, so that's why I was confused.
You know what, I think they're equal to each other. Let's see if we can, because this is gonna take a little work, I wouldn't have done this one. So if we multiply these two exponents together, we add their exponents, right? So that's really e to the 0.001 minus 0.002 t. So let's factor out our negative 0.002, which is what we had. So this is going to be e to the negative 0.002. Now, this is going to be just the t. So when you factor this out, you divide by this number. So when we take this and divide it by what we're factoring out, we're going to have 0.001 divided by a negative 0.002, which is going to be a negative a half, which is our minus 0.5. So we were actually agreeing. I don't know why they would write it that way. I think that's not the way I would think to get there. So my guess is they started where we were and then broke it apart to get to there. I wouldn't do that. But we agree. What else? To 130, right? Okay, so let's take a look at our order of magnitude worksheet. So I want to work through that, and hopefully we'll have some time where we can do some practice problems. If not, there are some practice problems in that video that's in the supplemental materials. Okay. So normally what we would do here, I would have you do this as we would get into groups of 3 to 4 and work on it together. That's going to be a little difficult in our time where we are. So I'll try to get you started, and I want you to, part of this is to do a little discovery. Okay, so we're going to talk about this idea of order of magnitude. And we talked about it, and this is of functions. So we talked about this a little bit in the context of different power functions or polynomials. So it's relatively easy to determine which of two polynomials is a higher order function. So if we have f of x equals, say, x to the third minus 4x squared plus 11, and g of x is going to be x to the fourth minus 2x plus 3. At a glance, we can tell which of these is the higher order magnitude function just by looking at the highest power. Okay? So 4 bigger than 3, that's it. It's when you compare these two, again, we're talking about when we look at their end behavior, the higher order magnitude function is going to dominate the lower one. It is going to grow much bigger, much faster than this one. That's an important idea. Now, it's pretty clear and straightforward when you have polynomials or power functions. We want to go beyond that today and compare polynomials. Well, we'll talk about power functions, but really, so, something, we've talked about y equals kx to the p. That's what we mean by a power function. But what holds for power functions generalizes to polynomials. Because all that matters in a polynomial is the highest power of x. And so once you ignore the rest of it, now you're really just looking at a power function again. So what's true for power functions is also true for polynomials. But then we want to also compare them with exponentials. Remember, this is going to be something like y equals a b to the x, or in our world, we kind of like to think PERT, because a lot of times, most of the time, we'll be dealing with an Euler's number exponential, and then we want to compare that to logarithms as well. So we know who's the big dog when we talk about power functions or, two power functions or two polynomials. The next question we want to go is, well, what if we're going to compare them between these kind of groups? Which one is going to grow bigger faster? Which is the higher order magnitude function? So on the front page of this, if you read through this, what it's saying is that this can be important. In past AP exams, there have been questions that involved some kind of comparison between, the one in particular here is y equals 2 to the x and y equals x squared. So the way this comes up is, it's not really just saying what's the order of magnitude, but understanding the order of magnitude is important. Because when this was posed on an AP question, an earlier free response question, it was finding the area between the two curves, which is something that we'll do quite a bit in here eventually. So the idea then is, give these a couple different colors. So if you understood order of magnitude, you would have a much better chance of getting this correct. If you didn't, and it was a calculator active problem, you would probably graph this on a standard 10 by 10 window. And what you would see is that initially, the power function looks like it's getting bigger faster. It just comes out of the gate faster. And if you were graphing on a 10 by 10 window, the 2 to the x, would do something like this. And so what happened to a lot of people on this problem is that they did this, oh, I got it. There's the region I'm trying to find the area. And so then they went and do whatever you have to do. We have to learn the calculus to do that first. And they could find the area of that region. The problem is that 2 to the x is actually a higher order magnitude function than x squared. And if students recognize that, then if they knew that going in, they would know that the 10 by 10 screen wasn't telling the whole story. And they would have expanded their graphing window, and they would have seen that eventually, now you have to kind of give me a little artistic license here. This thing is going to get much steeper. Just kind of like a time warp there, it's a wrinkle in time. So use your imagination. The idea is that eventually the exponential is going to get so steep that it's going to come back and intersect the x squared a second time, third time actually. And it's actually over the long haul, as we go to infinity, this exponential is going to dominate the x squared. It is going to grow much bigger, much faster. And if a student recognizes that, they'd say, oh, I'm going to play around with this window. So really what I have to do is I have to find the area of this region. And there's a second, it's going to be more like a sliver when this is done to scale. There's actually two pieces of area that you have to find. But you would have had to have known that whole order of magnitude thing first. So what we're going to do on this worksheet is a nice way of looking at the order of magnitude is to take the two functions that you're comparing. So you're going to say, here's two functions. If I call this one f and I call this one g, the question is f a higher order magnitude function than g? Is g higher order magnitude than f? Or are they the same order of magnitude? And so a nice way to do this, what I want you to do on this worksheet, and we'll collaborate by talking to each other, across the room, safely distanced here. We want to look at the limit as x goes to infinity of, and then we'll compare those. So we'll do the ratio of f of x over g of x. So what you're going to see on your calculator, and you may have to play with the window sometimes, some of these are not obvious. And you may see that it does something like, whatever it does in here, and then it blows up. If it blows up, which one's getting bigger faster? The numerator function or the denominator function? The numerator is overpowering and dominating that. So if your graph eventually takes off, it'll take a little while. What happens in here isn't really of importance. What happens once we really establish who's the king of the hill? This means that f would be a higher order, see that? Higher order magnitude function. Now, if g was the higher order magnitude function, what would the graph look like? G is getting way bigger, way faster than f. What's going to happen? Yeah, it's going to get crushed to zero, right? So it may take off a little bit, and then it's going to get smushed down to zero. That means g is going to be a higher order magnitude function than f. You with me? I need nods of heads. What happens if they're the same order of magnitude? What is the graph going to look like? Well, it's going to become horizontal. It's going to have an asymptote, not zero. Horizontal asymptote, not zero. It may do, I don't know, but it's going to settle down and start to look like that. In that case, that we say that f and g are the same order of magnitude. So I'm writing equals, but not that f is equal to g. That's not true. They're the same order of magnitude. So, like in a polynomial, we would see the same order of magnitude if you had something like f of x equals 3x squared plus 2x minus 1, g of x equals x squared plus 4x plus 7. Same power of x. So as x gets really, really big, anything that's not an x squared becomes irrelevant. And it's going to level off at, if you have f over g, it'll level off at 3. And if you have g over f, it would level off at 1/3. Does that make sense? But you can get a horizontal asymptote, not 0. If it goes to 0, that means the denominator function is crushing the numerator function. Okay? All right. So that gets us through the front page. What I want you to do is to flip over to the next page. And we're going to kind of talk about this together here a little bit by little bit. So what I'd like you to do is you have number 1, part A, part B, part C. So you can work, talk, collaborate, but let's make sure that we agree on what the result should be before you go on to number 2. Okay? And so you're looking at the limit as x goes to infinity of natural log 3x over x to the 3rd. Graph that on your calculator, see what it does, see then, I don't know what they're talking about, this whole L'Hopital thing, that's weird. Anyway, evaluate that limit. So is that limit going to be 0, infinity, something other than zeros, 5, 2, something like that? Go ahead. Use your calculator as a way of discovering this. And you can compare your answers with your neighbor. And I'll warn you, B is tricky. You're going to have to be a detective and play with your window to get the definitive correct answer on B. I can't believe I have to ask Katie McPherson to talk. It's probably the first time ever. Now B, I'm just warning you, if you say B, if you see on your screen that it's taken off, you gotta expand your X max. I think you have to go to about 50 or something like that for an X max on part B to see the true story. Did you do that, Alan? Did you graph B yet? Oh, well, hurry up. Did you graph B yet? Well, guys are way pokey here. Think we got to the B yet? Okay, let me see. Oh, you got it though. What was it? Yeah, I think you go with an X max of 50. The red one?
Yeah, and then I did 500 a minute ago.
Oh, okay. So I think to see the true story on B, you want to use an X max of 50.
Oh, I think I know.
So choose X scale from the other one to 1 for this. You have that push that down?
Yeah.
So pick up another A X then go to the faster.
But it goes down.
Exponential. You did it for submission. Can we talk or we still need another minute? Just talking about the numbers 1, ABC. We all got ABC on number 1 yet or no? So the first one, what did you get that limit is? 0? Which means which is the higher order magnitude function? Yeah, so that power function is a higher order magnitude function than that logarithm. So we're trying to establish a pecking order here. Now in B, when you started out the gate, x to the 10th was took off, but if you go out to 50, it comes crashing down, right? Because give it a little bit of space, that exponential is going to overpower that power function. So what we're trying to say, the limit is going to be 0, and it's that denominator function, exponential, is a higher order magnitude than a power function. And the last one, because you know that that's like x to the 1 half over x to the 1, so the higher order function is going to be the one with the bigger x1. So the limit's going to be 0. Okay, can we answer number 2? Can you rank those? Smallest to biggest. It's like a food chain, right? So who's the one that gets sand kicked in its face all the time? Okay, which is the one that everybody else bullies, that everybody else can beat up on? The slowest growing one. Just try to put it into real life terms here. Something we can relate to. So which one is the slowest growing of the functions? Logarithms. They're pokey. Next, power functions. And the king of the hill is the exponential. So the takeaway from this is that an exponential will be higher order magnitude function than any polynomial, any power function. So even if you had like, 2 to the 0.1x compared to x to the million power, given enough time and space, that exponential is going to overpower the power function. Crazy. Okay, look at number 3. So you look at the graph, this is a graph of f over g. Which is the higher order magnitude function on A, f or g? Good. And looking at B, which is the higher order magnitude function? Trick question, they're the same, right? There's neither one that's higher. And part C? G. Good. Denominator function. So, going back to that question that was posed on the other page, how many times do the graphs of y equals 2 to the x and y equals x to the second intersect? 3. And that's going to be true of any exponential and any power function. Now, here's where it gets crazy. Given y equals 2 to the x and y equals x to the 100, how many times do we know the graphs are going to intersect? It's got to be 3, because exponential is a higher order magnitude function, and that's the answer to B, how can you support it? Now, I'll give you a clue. You're not gonna be able to get this on your graphing calculator. It happens too far away. So, I don't know if I can do this in 2 minutes. So we know that, we got this thing, and so we've got, what is it? 2 to the x and x to the 100. So we have 2 to the x and x to the 100. So 2 to the x is doing this, x to the 100 does this. So we've got our first 2 points of intersection. It looks like this one's out of the ballpark, but just wait, go far enough. And eventually this is going to catch up to that one. How can we convince ourselves of that? Well, here's the idea. I think if I let x be 100, so my claim is that eventually this is going to get bigger than that. Okay? See how you do that. So x to the 10, when I plug in 100, this is, I think I want to put in 100 or 1,000. I think I want to go to 1,000. So when I use 1,000, this is going to be 1,000 to the 100th power. Now, 2 to the 1,000, I'm going to think of it as 2 to the 10th to the 100th. Right? Because raised to power 2 power, you multiply the exponents. 2 to the 10th is 1,024. So by the time you get to 1,000, 1,024 to the 100 is going to be bigger than 1,000 to the 100. Crazy? I don't think you can do that to that. You got your review worksheets. Sorry, I didn't get time to work more problems, but you can look on the support materials in that video. You will see some practice problems.
Could I ask you a question on this? So on B, I see that it comes back down for the 100, but how would you calculate?
So the limit is
Yes,
so that's right on the.
so I would
So you would just say the limit is equal to.
okay, and so that was it for all of
In
them.
all three of them.
Okay,
Which means that the denominator, the denominator function, each of those is the higher order.
so if they were equal, then it'd be like X, or 1 equals 3.
Something.
Okay, thank you.
Yeah.
I know I'm not gonna be here next Friday for the test,
Okay.
but I have multiple meetings on. So I was wondering if on not the Monday coming, but the Monday after the test, I could just come in for third and fourth.
I thought it was second and third one,
Yeah, second and third.
because I have planning second and third, so that would work better.
Okay, yeah, that's fine.
Yeah, and then you just come in here and type it in here.
Yeah.
It'll just be awkward, me and you sweating bullets and we chill.
Okay,
Okay,
that's fine.
sounds good.
Oh, and
Sorry, I have another question. Okay, so to prepare, can I come in for those kind of next week?
I'd rather save my planning page, because I am so behind on right now. We can do before after school.
Yeah. Okay, that'd be great.
Any of those things.
Okay, thank you.
Mr. Street, can I get a few more of these?
Yeah.
That'd be alright.
Oh, yeah.
And like she asked, what's your availability for after school?
Before school, after school.
Okay.
all day is good.
Yes, sir. Sounds good. Have a good day, Mr. Street.
Thanks.